I want to talk today about light, and before we look at any calculations or anything like that, we need to look at some of the basic features of light. For instance, light travels in waves, and like the wave shown here, and there are a couple of features about that wave that we can talk about. We could talk about the amplitude, which is basically how high up the wave goes, but more important is the wavelength. The length from the top of one peak to the top of the next peak. That's a measure of some fundamental properties of the light. And wavelength is actually given a special symbol, and that symbol is lambda, represented here by the Greek letter lambda, or L. It's the Greek letter L, lambda. Now, different samples of light can have different wavelengths. Like in the example shown here, we've got one example of a light wave with a very short wavelength. The distance between one peak and the other peak is very small. And we have other examples with progressively longer wavelengths. The difference between one peak and the next peak is larger. So we've got shorter wavelength and we've got longer wavelength. We could also talk about these samples of light not in terms of the wavelength, but in terms of the frequency of the number of times we go through this cycle. What you'll notice is when we have a really short wavelength, we go through a lot of cycles really quickly. In other words, this cycle, the up and down, is very frequent, high frequency. On the other hand, when the wavelength is longer, it takes a longer time to go from one top up to the next top. So that's a lower frequency. Short wavelength has a very high frequency. It repeats very quickly or frequently. The longer wavelength has a low frequency. As we said before, the wavelength has the special symbol lambda. Frequency also has its own special symbol. It's the Greek letter nu, even though it looks like a V. So this is the symbol for frequency. This is the symbol for lambda, where lambda is wavelength. And depending on the wavelength or frequency, we have different types of light with different types of property. For instance, radio waves have very low frequency, very long wavelength, whereas gamma rays have very high frequency and very short wavelength. Somewhere in the middle, there's the visible light, the light that we can see. And depending on the color of the light, have different wavelength or different frequency. Red light has a longer wavelength and a lower frequency, whereas violet has a shorter wavelength and a higher frequency. When we do calculations with light, there are two equations that we're going to work with. The first is E equals h nu, where E is energy, h is Planck's constant, and this is the frequency, where Planck's constant has the value 6.626 times 10 to the negative 34th joules times seconds. It's also important to remember that the units on frequency are second to the negative 1. So if you're asked to find the energy of one photon of light, and a photon is what we call the packet of light energy, you can use this equation. So we could answer the question, what is the energy of light with a frequency of 1.50 times 10 to the negative 14th hertz? Just remember that hertz is just a fancy way of saying second to the minus 1. So hertz equals second to the minus 1. Well, I'm just going to plug in my information into my equation. So Planck's constant times my frequency, and the seconds cancel out, and I'm left with energy. And the answer comes out to be 9.30 times 10 to the negative 20 joules. Now, if you're not given the information about light in terms of frequency, if you're given it in terms of wavelength instead, you need to get to frequency before you can find energy. And there's a relationship for that as well. And that relationship is C equals lambda times frequency. And what C is the speed of light. And the speed of light is 2.9979 times 10 to the 8th meter per second. And that's equal to the wavelength times the frequency. Now, notice that since the speed of light is in meters per second, frequency has to be in second, 1 over seconds, reciprocal seconds, and wavelength has to be in meters. So if I'm given information about light in terms of wavelength, I can use this to find the frequency and then find the energy, because I can rearrange this equation. If I divide both sides by the frequency, frequency cancels on the right side, and I'm left with wavelength equals speed of light divided by frequency. Or I could do it differently and divide by wavelength and get an equation for my frequency where C divided by my wavelength equals my frequency. I can convert between frequency and wavelength using this relationship. And this is the one that's going to be most useful for me right here. And that's the one I'm going to use in this next question. Let's suppose we have the following thing we want to figure out. What is the energy of light with 454 nanometer wavelength? Well, there are going to be two steps in this process. One, convert to frequency using this relationship we just found. The thing we need to be careful of is this is in nanometers, speed of light is in meters, so we have to convert this to meters. The easiest way to do that is to remember nano equals -9, so 454 nanometers equals 454 times 10 to the -9th meters. My frequency is going to equal the speed of light divided by my wavelengths, and that is going to equal 6.60 times 10 to the 14th second to the -1. Now that I have my frequency, I can use this first equation to find my energy, just plugging this number into the first equation. So my Planck's constant, my frequency, and when I plug that into my calculator, I get 4.38 times 10 to the -19th joules.